There is a theorem from geometry that I would like to show you. It's a really important one. I think it's up there with the Pythagorean theorem, but it's much less known. Maybe that's not right. So here it is. You know that a circle is a set of all points equidistant to a fixed point. And so in circles, if you start connecting the center of the circle with points on the circle, we're going to get lots of isosceles triangles because lots of sides will be just the radius. Okay. So suppose we're looking at, this is a diameter, D is the center of the circle. So AD and DC are both radii in the same circle, therefore equally long. Okay, then ADC is an isosceles triangle. Then the angles opposite these two sides are also equal to each other, so we can safely conclude that these two angles are equal to each other. Let's call them alpha. We're going to make the same argument for triangle CDB. Line segments DB and DC are equally long because they are radii in the same circle. And therefore, triangle DBC is isosceles. And therefore, the angles opposite the equal sides are also equal to each other. Let's call those beta. Nothing earth-shattering happened so far, right? So now all we're going to do is we're going to state that the three angles add up to 180 degrees for the triangle ABC. So the angle at A is alpha, the angle at B is beta, and the angle at C is alpha plus beta. And those add up to 180 degrees. You drop parentheses, combine like terms, clean up. And we get that twice alpha plus twice beta is 180 degrees. And therefore, alpha plus beta equals to 90 degrees. And that means that this is a right angle. You see that's alpha plus beta. So let's start with the definition. Suppose line segment AB is given, and we draw a circle of whose diameter is AB. So that can be easily done. You're given line segment AB. First, you have to find the midpoint. And then the midpoint will serve as the center of the circle. The half of the length of the line segment, the distance from the midpoint, is going to be the radius. This circle is called the Thales circle of the line segment. Well, let's see what Thales' theorem will address. Suppose you have a line segment AB, and you want this to be a side of a right triangle. Well, which side? If you want the right angle at A, that's easy, done. If you want the right angle at B, that's easy, done. But what if you want the right angle at C? What if we want this to be the hypotenuse? Where are those points? Where are those third points that if we connect them with A and B, there is a right angle at that point? And the answer to that question is they are all on the Thales circle. So you take the Thales circle and you take any other points than A and B, and what you're going to generate is a right triangle with AB being the hypotenuse. It's pretty amazing fact. More is true. If you actually go outside the circle, that's where you get acute angles, less than 90. And if you go inside the circle, that's how you're going to get angles bigger than 90, also called obtuse angles. So Thales' theorem states that given a line segment AB, if we wanted that to be the hypotenuse of a right triangle, then all the possible third points are on the Thales circle of the line segment. First of all, it's amazing how simple the proof was, and it's amazing at how many situations it pops up. And by the way, this is true backwards too. So if you have a line segment and you draw its Thales circle, then every point except for A and B will generate a right triangle, and all the right triangles are here. You can get some mystery other right triangle not on the Thales circle. So it's an if and only if. ABP is a right triangle with 90 degrees at P, if and only if P is a point on the Thales circle other than A or B. Thank you for watching.